trees on Majorca. And it was regarded as the causal agent of death and decline of these trees over the last 15 years. This is a bacterium endemic of the Americas and is regarded as one of the major threats of plants worldwide for its large number of vectors, clones, and hosts. So here we can see an infected field in Puigpunyent of almond trees, and here a close-up image of the leaves of an almond tree that has been infected. So what happens in a tree with, or in a plant infected with Xylella fastidiosa is that the bacterium form a biofilm in its xylem, forming clots that may block the nutrition of the plant and eventually cause the death of this plant. So this bacterium in nature is transmitted from plant to plant via vectors that are insects, which are xylem feathers. In Majorca, the main vector is the Philenosus spumarius, and this vector is a xylem feather which has a characteristic mouth part known as a stylet, which has the ability to reach inside the xylem vessel of the tree and feed from there, and it is in this feeding process that the bacteria is interchanged between vector and tree. So Philenosus spumarius has a 1-year life cycle, and the adult life of it spanning from April to at most December, and is in this time that when they can transmit the bacteria. Moreover, Philenosus spumarius has been known to have a great flight performance, so they can move within the field. So now we are going to present a model with this deterministic mean field description, a compartmental model for the transmission of this disease. So in our model is based on the models of Balearic and Castillo-Chavez with some changes. First of all, we have a population of susceptible hosts that get infected at rate beta when the interaction with an infected vector and become infected hosts. And then they move to the compartment of removed hosts because they die at rate gamma. And we don't consider natural death, as we consider that the time scales of the disease are much shorter than the demographic time scale of the host. We don't consider natural recovery, and we consider that the trees are not removed from the field that usually happens in Majorca. As per the vectors, we have susceptible vectors that become infected vectors at rate alpha when interacting with hosts. Is the only way vectors can get infected. And they also, the time scale, we also include the death rate of vectors because of the time scales, and we consider that it's the same for susceptible and infected because we consider that the presence of the pathogen is not lethal for the vector. And finally, we have added a birth rate for susceptible vectors, and with the model of Balearic and Castillo-Chavez, this birth rate may be different with the death rate, so they might not be imbalanced, and the population of vector may depend on time. Okay, and we don't consider a latent period because of field observation. So these are the equations of the model. All parameters are positive. So first, one analysis that we can make is that first of all, we know that the population of hosts is constant. So one of the equations can be disregarded, and then, but the population of vector is time dependent with this time dependence and with this stationary value. So now for the initial conditions, we always are going to understand the introduction via the host because this was happening in Majorca. So initially the infected vectors will be always 0. So this, no matter the parameters, this will always be fulfilled. So then we can define the epidemic outbreak in this way. If the derivative of infected host is always negative, we say that there is no outbreak. And if at some point of time, that may be not at the beginning of the dynamics, because at the beginning of the dynamics it will be always negative, but at some point it's positive, we say that an outbreak has occurred. So we are going to see two cases. First, the general case for delta greater than 0, and then the extreme case where delta is equal to 0, that this will account for one year cycle, that then this model may be iterated for account for larger periods of time. So first of all, for delta greater than 0, it's customary of this kind of model to start studying what is known as a disease-free equilibrium, which may be a pre-epidemic state with no infected individuals, in this case with no infected hosts and vectors. A particularity of our model is that not any pre-epidemic state that is disease-free is an equilibrium, because as the vector, the population of vectors is time-dependent, the only equilibrium is when the population of vectors is at this stationary state. So the pre-epidemic states are disease-free and in equilibrium with this term, it's at its stationary value. So now we can make a linear stability analysis of this disease-free equilibrium, and we see this threshold condition. If this combination of parameters are less than 1, it's stable, and if it's greater than 1, it's unstable. So one parameter that is used to characterize to quantify whether or not disease will spread into a population is usually the basic reproduction number, which is the number of secondary infections caused by introducing a single infected individual in a whole susceptible population. But for vector-transmitted disease, we have to make an assumption that whether the transmission from host to vector to host is either one or a two-step process. We understand it as one-step process because we understand that we are interested in the infection of the host, and we see the vector as only a means of transmitting the disease. So if we, with this supposition and using a method of the net generation matrix method, which relies on the linearization of about the disease-free state. Remember that this is disease-free state. We get that the basic reproduction number for this model is this one, and we see that the threshold we recover is the same than from the linear stability analysis. So another thing that we can do is a fast-slow approximation of this model. It's interesting to reduce the dimensionality because we have 4 equations. So, what we do is that suppose that the death rate of the vector mu is a large parameter compared to the others. So we can write the 4th equation like this, and then the other equations have this form. So now we have 3 equations, but we can further reduce this dimensionality to 2D via the explicit expression of NV. And these are the equations we recover. We see that this is a SIR model-like with time-dependent coefficients. And we also see that this system is non-autonomous because it has an explicit time dependence with NVT, except for the cases that the initial population of vectors is already in its stationary state when the system is an autonomous one. And all the tools of autonomous systems can be used in here. So from this, we link what we said before, that we can only use the linear methods when the initial population of vector is in its stationary state. If not, generalization of the net generation matrix is needed, and as some authors had done to study this case. So next, we can study the case delta equal to 0. And in this case, it's a special case because at the stationary state of the system, the vector population is 0. So any linear stability method will tell you that there can be no propagation of the disease because you need vectors to propagate the disease, and in the stationary state of the system, you have no vectors, so there can be no transmission. However, this is not what happens because at the beginning of the dynamics, you have a system that is not in its stationary state, and it can transmit the disease. In fact, we have numerically seen that outbreaks are possible even if the linear stability analysis doesn't capture it. So other tools will be needed to understand this. However, it is also interesting to study this system because we can find a non-trivial conserved quantity of the system that we can use to make an exact reduction of the dimensionality instead of an approximated one. So we can reduce it via this conserved quantity that we have derived to a 3D model, and further to a 2D model with an explicit time dependence, using again the the expression of NV. So now we can see some numerical results, also for delta greater than 0 and then for delta equal to 0. So here, as an example, two realizations, one above threshold and another below threshold. From the above threshold, we see that this orange line that is the infected host that has an initial decrease and then an outbreak, and in the below threshold case, it's monotonically decreasing. So then we want to check the validity of the threshold parameter R0, and we study parameter by parameter the effect of the threshold. So I'm going to explain for alpha, and all the others are the same. So here what we do is to define the critical parameter when R is equal to 0. We find this expression, we give numbers to this parameter so that the critical value of alpha is 1, and then we do realizations for different values of alpha and compute whether or not there is a maximum on the infected host. If there is a maximum, and if the first alpha that this behavior change from no maximum to maximum or from maximum to no maximum is the critical. So, and we see that the value coincides pretty well with the expected, with a relative error of 0.5%, and the same for all the other parameters. So we say that the R0, in the case where here we have used that the initial condition of vectors is in its equilibrium state, it's fulfilled. We want to explicitly check the effect of having a distinct ratio delta mu, because we said that this is an introduction that is different from what Brauer and Castillo-Chavez done. So we again repeat what we did before, but for distinct values of the ratio delta mu and for distinct mu. So we fit all parameters but beta, and we compute at which beta there is or not an outbreak, and this is the R0 that we get, and we see that it fulfills the expected values, and here are the betas that we've used, and the black line is the theoretical one. So we see that it's in good agreement. So next, a more interesting case is when the initial population of vectors is not in its stationary state at the beginning of the dynamics. So in here, and we've computed distinct realization of this case, and these are the R0s that we get. So we see that for values of the initial condition below the stationary value, the R0 computed with the linear methods can be used, but for values of the initial condition greater than it, the R0 is not representative of the model, and we should call it R0 star with a value P that will account for the difference in this initial condition. So we can understand this difference for below and above if we see these two plots that we put as an example. This is below. So below, we see that the population of vectors goes to its stationary value at some point, and that this is what enters in the R0 value. So at some point of the dynamics, the conditions of the linear stability analysis are fulfilled, and so there can be an outbreak. So at some point the conditions are fulfilled, and then well, you can use this. However, for the value of the parameters, the initial conditions larger, what happens is that there is a non-vanishing period of time where the number of vectors is larger than the one expected. So you need less value of the parameters, of less value of this beta, for example, in order to transmit the disease. For this reason, R0 is smaller than 1 and not greater or equal. So we have repeated for distinct value of delta mu. We see the results are pretty similar. And then we finally we check numerically the validity of the time scale approximation that we've done. This is for a value of R0 above threshold, but we've done it for below threshold, and we've done it for other value of the parameters. And we see that as we increase mu, that is the death rate of vectors, the dashed lines, which are the lines of the realization computed with the approximated system and the solid lines, which are the lines of the model computed with the complex system without any approximation, start to become equal, and we can further see the mean error of the EV, that is the function that we have approximated, that it decreases when we increase mu. So we see that, well, the approximation works well in when mu is larger. So finally, we do realizations of delta being equal to 0, and we said that even though we cannot use the linear stability analysis to compute an R0 because it will give us that there is no threshold, we present some realization where the disease in fact can spread into the population. Here we see a peak, that is what we've defined as an epidemic outbreak, and here that it decays. So this is here there is no outbreak, and here an outbreak. In this plot we also show that two lines, the solid lines being the full system, and the dashed line being the exact reduction that we've done with the conserved quantity C. So with these plots, we also show that this conserved quantity, in fact, is conserved, and because the two results are in good agreement. So what we've seen so far, so we've done a compartmental midfield model for Xylella fastidiosa, which couples host and vector. For host, we have introduced three compartments: susceptible, infective, and removed, and we've used a constant population. For vectors, on the other hand, we have used two compartments, susceptible and infective, and we've included their death and birth rate for them. We've done several reductions of this model, one via fastest slow approximation, which leads to a time-dependent SIR model for the host, and an exact reduction has been done in the case of delta equal to 0 by means of a conserved quantity that we have derived. Next, we have also seen we've computed the basic reproduction number via the linear methods, and we've seen the validity near the disease-free state, and we have also seen that the generalization of this method is needed when the vector population is not in its equilibrium state at the beginning of the dynamics. So at future work, we'd like to incorporate the vector seasonality by repetition of the 1-year cycle when delta is equal to 0, so repetitions, which must include climatic effects, as the population of vectors at the beginning of the dynamics would depend on the climate of this year. Generalization of R0 are needed to be included for vectors not in the stationary state of the dynamics, and then finally we could compare with file data when we could compare with file data if we have this done. So, okay, thank you very much, and do you have any questions?
So we'll start with the questions then, and start with
okay. So thank you. I have a couple of questions.
Yeah.
Very interesting. Well, first, I like the name of the document. It was very well written. So congratulations. Yeah. Saying nothing.
Can I have? It's okay. I don't know.